the Pythagorean theorem. I have this right triangle that's rotated and reflected to end up creating a square. And I'm going to look at the area of the square compared to the area of the parts that compose the square. And I'm going to be able to put those together and simplify to be able to get a squared plus b squared equals c squared. So let's try this out. First, we're going to look at the area of the square by itself. I know that area of a square is the length of one side times the length of that side. So the length of one side is c, so I know that the area of the square is c times c, or c squared. Now let's look at the area of one of these triangles. So the triangle's over to the side that's labeled. It's the same one that's in the square. And this is a right triangle. I know that the area of a right triangle is 1/2 times its base times its height, which is 1/2. Its base is a. The length of its base is a. And the height of it is b. I want to use the two sides that are not the hypotenuse for this. So I know the area of one triangle, so now I can find the area of all four triangles. I can just multiply it by 4. So the area of all four triangles is 4 times 1/2 AB. And I can simplify this. 4 times 1/2, I can rewrite as a fraction. Cross simplify, so 2 goes into 2 one time, and 2 goes into 4 two times. 2 times 1 is 2, and I still have AB. Now in order to find the area of this inner green square, I need to know what the length of one side is. So if I know that this length right here is B, and I know that this length right here is A, the length that's left over is the length of the side of the square, which would be B minus A. So the area of this inner square would be B minus A times B minus A. And now I want to go ahead and multiply this. So I have two binomials multiplied together, so I need to double distribute. So first I'm going to multiply b times b, which is b squared, and then b times negative a, which is negative ab. Then negative a times b, which is, again, negative ab, and negative a times negative a, which is positive a squared. When I double distribute, I need to make sure that all parts of each binomial are multiplied together. So now I can simplify this and combine like terms. B squared is just by itself, so I'm going to bring that down. But I have negative AB and negative AB. Those you can simplify to negative 2AB, and I'm going to bring down that a squared. So I know that the area of each part of this square is equal to the area of the square. So I know that the area of the four triangles plus the area of that inside square is equal to the area of the whole square. So I'm going to go ahead and set that equation up and set them equal to each other. So the area of the four triangles I already found is 2AB, and the area of that inside green square is b squared minus 2ab plus a squared. And if we look back at the first area we found, the area of that whole square is c squared. Now I can simplify this. I have a 2ab and a negative 2ab. Those will cancel out. And so on the left side of this equation, I'm left with a squared plus b squared. And on the right side of the equation, I am left with c squared. This is my Pythagorean theorem, so I am done. Moving on to the next proof. This one looks a little bit more difficult because there's more we have to find, and there's two whole squares that we're looking at, but this is something that I know you can do still. And this is the proof that Pythagoras himself used to prove his own theorem. So to start off, let's go ahead and label these. Let's label this first square number 1 and the second square number 2. So first we're going to find the area of square 1. So once again, I need to know the length of this whole side, which would be a plus b. So the area of square 1 is a plus b times a plus b. Now let's look at a triangle. All the triangles in this square are the same. All the short legs are a length of a, all the long legs are a length of b. And then we don't need to know the hypotenuse because it's not going to matter to us. So once again, just like in the first proof, the area of this triangle is 1/2 times the base times height, which would be a times b. And there's 4 triangles in this square, so we want to know what the area of all 4 triangles are. So once again, I'm going to multiply the area of one triangle times 4. And once again, this will simplify down to 2ab. Next, I want to find the area of the green square. I know one side length is a, so the area of that square is a squared. And now I want to do the yellow one. The side length is b, so the area of that square is b squared. So now I'm going to put those parts together to find the area of square 1 and write it in a different way than we previously did at the beginning of this proof. So first I want the area of all 4 triangles, which we found to be 2ab, plus the area of the green square, which is a squared, so we're just going to add it up, and the area of that yellow square, which is b squared. Now let's move on to square 2. Once again, one side length is a plus b, so the area of this square is a plus b times a plus b. The area of a triangle is 1/2 base, which is a, times the height, which is b, in the area of 4 triangles. So you're going to multiply that by 4. So you'll have 4 times 1/2 times a times b, which once again simplifies to 2ab. Are you seeing any patterns in this yet? So now let's look at the square that's inside of that big square number 2, one side length on that square is length C. So the area of the square is C squared. And now let's write the area of square 2 in a different way. So the area of square 2 is the area of all 4 triangles plus the area of that inside square. So the area of all 4 triangles is 2AB plus the area of that square, which is C squared. Now, the reason we wrote that the area of square 1 is A plus B times A plus B, and the area of square 2 is A plus B times A plus B, is to show that they're actually equal. Because we can say that A plus B times A plus B is equal to A plus B times A plus B. So we know that the area of square 1 is equal to the area of square 2. So we can set the areas equal to each other, which is when we want to use the second areas that we found, which for square 1 would be 2AB plus A squared plus B squared. And we can set that equal to square 2, which is 2AB plus C squared. Now, you may or may not look at this and see what we can simplify out of here, but you should be able to look at it and see that we want A squared, B squared, and C squared. So let's try to subtract out a 2AB. There's a 2AB on both sides, so that'll cancel out on both sides of the equal sign. So on the left, I'm left with A squared plus B squared. And on the right side, I'm left with C squared. I have A squared plus B squared equals C squared. So I have the Pythagorean theorem. I am done with this proof and ready to move on to the next one. On this last proof, I'm going to do another similar thing as I did in the first 2 proofs, but this time I'm going to look at area of the outside triangles plus the area of this inner square to equal the area of the whole big square. So first, I want to find the area of one green triangle, which is the same as this triangle that's off to the side here and labeled. So I know the area of this triangle is 1/2 base times height. Base is A, height is B. Pattern is still continuing from the first and second proof. Now the area of all 4 triangles, I'm going to multiply the area of one triangle times 4. So 4 times 1/2 AB simplifies down to 2AB. So now I want to find the area of this blue square that's in the middle. Well, if I look at my labels, I know that the hypotenuse, which would be the side length of this square, I know that that length is C. So I know that the area of this blue square is C squared. Now I can put those together to find the area. Later on I will put those together to find the area of the big square. Right now I want to look at the side lengths that make up one side. So if you look at our labels and you label it, I see that this side length is the longer leg, so it's B. And this part of the side length is the shorter leg, so it's A. So the length of that whole side of that square is A plus B. So the area of the whole big square is a plus b times a plus b. Now I want to double distribute. So once again, I'm going to multiply every part by every part. So I have a times a, which is a squared, a times b, which is ab, b times a, which is once again ab, and b times b, which is b squared. Oh, I forgot my a squared over here. Now I can simplify my like terms because I have an AB and an AB. So I can rewrite this as a squared plus 2AB plus b squared. And now I want to put together those different parts of this square to equal the area of the whole figure. So I'm going to take the area of the big square, which I found and I know is a squared plus 2ab plus b squared, and I want to set it equal to the inside blue squared, which is c squared, plus the area of all four green triangles, which is 2ab. I look at this and see that I have 2ab on both sides of the equal sign, so I'm going to subtract those out of there. And so I rewrite this. I have a squared, 2ab and negative 2ab cancel out, b squared, c squared, and 2ab and negative 2ab cancel out again. So once again, I have the Pythagorean theorem here, and I am done with this proof.